Hello, here we are again. We're back for more fun. So today we get to start a new chapter in our lives. Very exciting stuff, you guys. This one, or this section anyway, is kind of, like it says here in this kind of fine print, we're trying to get kind of the hang of what polynomials are. We're going to study what they look like, and we're going to know everything about them. But before we kind of jump into the pool, we got to kind of test the water, put your foot in the pool, see how cold it is. That kind of thing. So first we're going to learn about exponents and their properties. How do exponents, if you have more than one exponent, how do they work with each other? If you have two exponents multiplied together, what do you do? All the kind of rules that we'll need to develop in order to really understand polynomials. So we're just kind of laying the groundwork for future stuff. And there's not really, a lot of introduction to this section. It's more, here's a rule, now practice it. Here's another rule. Now practice that. So that's kind of how this section is going to go. Let's look at the first rule here. In this first box, this rule is called the product rule. So it looks very, it doesn't look easy to understand, I think because they're trying to keep it really general. So notice they say a to the m power multiplied by a to the n power is a to the m plus n power. That's it's hard to imagine what the heck, where would I even see that? What's a? Is that a variable always? Is that a number? But I think when we do these three examples that are below, that'll really kind of help it sink in. But what it really means, if you want to think of it in words, is it says is part of the product rule. In other words, if you want to multiply powers that have the same base, and I guess if you want a visual of that, look at part A of example 1. You have 3 to the 5th power, whatever that is. You're multiplying that by 3 to the 4th power. So those have the same base. Base is, like if you have an exponential, something to the power, like say, what they're using is a to the m or a to the n. A is the base. So it's base, always think of base as the thing being raised to the power. A is the base. And then of course here m is the exponent, or power, I think power is kind of a slang word sort of for exponent. Exponent's probably more proper, but everybody knows what you mean when you say power. We know what that means. So when they say base, they mean the thing being raised to the power. And notice in this example, part A, 3 and 3, they both have the same base. So it's saying, if you want to multiply powers of the same base, like we have, 3 to 1 power times 3 to another power, you can write that as just 3 to 1 power, as long as you add the exponents. So if we want to combine those into 3 to something, it's going to be 3 to the first guy's power, 5, plus the second guy's power, 4. So it'd be 3 to the power of 5 plus 4, which is 9. And a lot of these problems, you can just leave it like that. I think they're just kind of wanting you to practice using these rules. They don't really care what the answer is. Because I imagine 3 to the 9th power is a pretty big number. So don't feel like you have to multiply everything out, especially when it's a huge number. I think if it was a smaller one, like say we did this problem and we ended with 3 to the 2nd power, for example, that one they'd probably have you write out. 3 to the 2nd power is 9. That one. But if it's really large, 3 to the 9th power, oh my gosh. I'd use a calculator for that one probably, and it'd be huge. You probably don't have to evaluate that guy. So in this section, don't really worry about it. Alright, we'll use the same rule to look at part B now. And notice part B, we have 3 different things being multiplied together. Negative 5 to the 7th power, negative 5 to the 3rd power. And then here, what's this guy? Negative 5... What would his power be? I guess it's like an invisible 1, huh? Because any number has an invisible 1 power, so it might not be a bad idea, because I think this will be helpful. I'm going to rewrite that last guy as negative 5 to the 1 power. And I do that because it says you can combine, as long as these all have the same base, and they do, all 3 of these have a base of negative 5, I can write this as just negative 5 to 1 power, as long as I add all the powers. So it'd be 7 the first power plus 3 the second power. And this is where it's good I wrote this guy as 5 to the 1 power, because I'd be thinking, okay, plus what? I mean, do I have to add anything else, or would I forget to do anything? You have to add the plus 1, because that really makes a difference. And if I add all those exponents together, that's 7 plus 3 plus 1 is 11. So it should be negative 5 to the 11th power. And this is another one, 5 to the 11th power, that's a huge number. Don't even worry about simplifying that. Just leave it. Don't worry about it. No problem. And it's going to feel weird because you're going to want to evaluate that. Because we've done, when we learned about order of operations, PEMDAS, you always do exponent first, so it's kind of in our minds we want to evaluate what that is. But there's no need in these problems, especially if it's a huge number like that. The 11th power, oh my gosh, that's a big number. Alright, let's try this last part of this problem, and then we'll move on to the next property of exponents. So this one looks more complicated. You have, notice something in parentheses here, there's a w to a power, but not only that, there's a z to a power, so two different bases there. One has a base w, one has a base z. And then in the next parentheses you have w to the 9th and z to the 11th. So you know what we can do if we want? I mean, you don't have to probably write this many steps out, but just kind of if you're kind of a cautious person and you want to be careful, I can rewrite this without parentheses. There's not really a need for those parentheses. Everything's being multiplied here. W times z in the first parentheses, all that multiplied by w times z in the second parentheses. I'm going to write this all out just, okay, w squared times z to the 6th, that's times w to the 9th, and that's times z to the 11th. You don't have to write the multiplication symbols, but I don't know, in my mind it kind of makes it easier. And now I'm going to think about, you know, when you're multiplying a few numbers like we are, well, these aren't numbers, these are variables, but you know what I mean. If you're multiplying a few things together, it actually doesn't matter what order they're in. So if I want, I think I'm going to write the w's next to each other, because I know I can only use the product rule if I have the same base. So I'm going to write the w's here next to each other, because I know I actually have the hope of combining those. And then I'm going to write the z's. There was a z to the 6th, and then there was a z to the 11th. Because I have no hope of combining. I can't multiply w to the 2nd power and z to the 6th because they have different bases. There's no way to do that. This property, the product rule, only works if they have the same base. So now that I've arranged them like this, I'm going to just take this and write it as 1w by adding their powers. It's 2 plus 9. And you could do that in your head. Don't feel like you have to write that out. You could just say, oh, 2 plus 9 is 11, and write 11. And then the same thing with the z. I'm adding the powers 6 and 11, and you could just add those in your head again. That's w to the 11th power, and z to the 6 plus 11 is 17. So that'd be your final answer there. And I probably wrote out more than you have to, but it's just to kind of show why this works. You know, why are you able to multiply the w's and then multiply the z's? Is that legal? Yeah, because we kind of showed why. You don't need the parentheses, first of all. You can rearrange things as long as they're all being multiplied. And then you can combine anything that has the same base together. But you know what we could have done in the very beginning looking at this? You could have just said, let me combine the w's. Okay, w times w, I'll add their powers and get 11. And then you could say, all right, what about the z's? Z times z, I'll add their powers and get 17. So really, now that we've seen why this works, you can just go straight from the original problem here to the answer. Don't feel like you have to really show any steps in the middle. It's just if you're one of those, yeah, like I said, really cautious people and you don't want to, take anything for granted or try to jump to conclusions. It is okay to do that, and we've kind of shown why. So all right, now I think we're ready for the next exponent property. This one's called the quotient rule. And if you remember quotient, the word quotient means divide. So that's what's happening here. I mean, in the product rule, remember we had the same base multiplied together. Now we have the same base divided. It's a to some power divided by a to some other power. If you're dividing two two exponentials with the same base, what you can do is subtract their powers now. So this quotient rule is really exactly the opposite of the product rule. The product rule said if you're multiplying bases, you add their powers. This time you're dividing bases, you subtract their powers. So it's like the opposite operations. Multiply becomes divide, addition becomes subtraction. But in other words, this makes it make more sense to me. To divide powers with the same base, you subtract the exponents and then keep the base the same. That's the thing, yeah, you don't want to say, I mean, it's not like, let's say if I look at part A in this example 2, I'm not going to say 7 divided by 7 is 1. You're not changing the base, only the exponent is changing. So in part A, they're saying, this is all going to be written as just 7 to 1 power. I'm okay to do this because they have the same base 7. And I'm taking the numerator's power, 8, and subtracting the denominator's power, 2. I'll just subtract. You don't have to write that out, but if you wanted to. 8 minus 2 is 6. There it is. And that's another one. 7 to the 6th power is a huge number. Don't even worry about multiplying that guy out. Not a big deal. All right, let's try the next one here. Part B looks kind of scary, but notice what's being raised to the powers in this one? X minus 2, that entire thing. That's what the parentheses are there for, to tell you it's not only the 2 that's being raised to the 13th power, or the 8th power, it's the x minus 2, that entire thing. So here the base is x minus 2, so whatever I do, it's going to be x minus 2 to some power. And just like in the last one, I'm going to take the numerator's exponent, 13, and subtract the denominator's exponent, 8. Let's see, 13 minus 8 is 5, I believe, right? And that's it. No need to try to simplify that. Actually, at this point, we don't really know how to simplify that. Well, we'll see that in a couple sections from now. How do you take two things being added or subtracted inside parentheses and raise it to a power? It's more complicated than it looks, so don't worry about trying to figure it out. You know, they're good with leaving it like that in this section, as long as you used whatever rule you're supposed to use to simplify it. All right, this last one looks kind of complicated, huh? You got a 9 over 12, and an A over A and a B over B. So you know what you can do if you want to? Kind of focus on what are like terms here. The 9 and the 12 are kind of like terms, you know, they're just constants, and I can probably divide those or simplify them. And then I'm going to focus, I see A's in the numerator and A's in the denominator. I want to give them their own little fraction separate from everybody else. And then the B in the numerator and the B in the denominator. That kind of makes it make sense more to me, or make it simpler, and then I can simplify either each of those three fractions there. So the first fraction, it's not really like I can use an exponent rule. 9/12, there's no exponents there, but I can reduce it as if it were a regular fraction. 9 over 12 reduces to 3 over 4. And then the next thing I have is what? A to the third. So I can write, since they're both A's, the base, I can write it as A to 1 power. So it's always the numerator's power, 3, subtract the denominator's power, but the denominator doesn't have a power. But remember, if you don't see an exponent, it's an invisible 1, so don't forget that. There's an invisible 1 power here. That's what you're subtracting for the A's exponent. And then I'll do similar things with the B's exponent. The numerator's exponent is 7, subtract, the denominator's exponent is 6. And I think we're almost done. We have 3/4, there's nothing really you can do with that. We're multiplying that by A to the power of, let's see, 3 minus 1, that's 2. And then B has an exponent of, let's see, 7 minus 6 is 1. And you know, this is pretty much as good as it gets, although I'd probably get rid of the little multiplication symbols. I'm just going to write 3/4 A squared B. And we know that a variable to the 1 power is just that variable. So I think leaving a 1 power there kind of makes it look sloppy and unfinished. I'm going to just leave the 1 power off and just understand that there's an invisible 1 power there. That one took a little thinking, but I think it really does help to kind of separate them. Think of them as 3 different separate fractions, so that way you know what's kind of like terms and what's not, and then simplifying those, and then combining them kind of in the end again. Alright, let's see. This last one, we have part D before we move on to the next exponent rule. Actually, this problem will kind of give us an idea of why the next exponent rule is the way it is. So this one looks kind of weird. You think, okay, it's x to the third over x to the third. So think about that. On one hand, that's what? Well, if you have the same thing in the numerator as in the denominator, that's going to be a 1, right? Because if you wanted to, you could go, let me write that out here. Let me erase that, sorry. Because what's x to the third? X to the third is x times x times x. And the denominator is the same thing, x times x times x. So you can kind of reduce, you know, this x cancels with this x, this cancels with this x, this guy cancels with this guy. There's nothing left, so there's automatically just a 1 left. So it's kind of strange. On one hand, I know that this is equal to 1, because any fraction where the numerator and the denominator are the same is going to be a 1. But on the other hand, since they have exponents, I can use the quotient rule to simplify this. Let's see, so I'm going to take, since they have the same base x, I'm going to take the numerator's power, 3, and subtract the denominator's power, 3. So it'll be x to the 3 minus 3 is 0. That's kind of interesting. So I knew on one hand this should be equal to 1, but using the quotient rule, I found out that it should be equal to x to the 0. So I guess it must be that x to the 0 is the same as 1. They mean the same thing, because when I simplified it one way, I got 1. When I simplified it another way, I got x to the 0. So that actually brings us to our next exponent rule. Let's see, the next exponent rule is basically that anything to the 0 power is 1. That's kind of an interesting one, huh? That's definitely one of those ones you just kind of want to memorize. doesn't really make a whole lot of sense when you think about it. Because, I mean, if you think about it, what's, like if you raise 2 to the 3rd power, something like that, that makes sense, because that means you multiply 2 by itself 3 times. Alright, I can understand that, but what if you raise 2 to the 0 power? What does that mean? 2 multiplied by itself 0 times? What the heck is that? So I don't think using reason or our old definition of exponent, that doesn't really make any sense as far as 0 exponents go. So this is something you just kind of want to memorize. We kind of make this a rule because it works with all our other exponent rules. It doesn't really make a whole lot of sense as far as what exponents really mean. So don't think of it that way. Don't say, oh, I'm multiplying something by itself 0 times, because that's just going to not make any sense at all. Alright, let's see if we can practice that. I know it seems kind of silly, but... So let's see, in example 3 here, part A, we have 127 to the 0 power. Well, 127 is a large number, but it says anything to the 0 power, no matter what it is. Here it says anything is a 1. And that's it. So the answer is 1. It seems like kind of silly, but that's okay. Now we'll look at part B here. Part B, though, has a negative, so I got to be careful. It's negative 7 to the 0 power. But the thing is, you notice that the 0 power is only on the 7. It's not on the negative. So it's kind of like negative, and then 7 to the 0 power is 1. Because here only the 7 is being raised to the 0 power, not the negative. 7 has the 0 power, not the negative. So the negative doesn't go away and just become part of the 1. The negative kind of stays along for the ride, and 7 to the 0 power becomes 1. The negative stays. So be a little careful on that. And it would have been different. Let's say I had been given negative 7 in parentheses and then 0. Well, that means that the entire negative 7, the negative and the 7, are both raised to the 0 power. That would make it a 1. No negative, because the negative was part of what was being raised to the 0 power. So keep that in mind. Parentheses really make a difference. And we'll see that actually here in part C and part D. So notice in part C, it's 3x parentheses to the 0 power. That means the entire thing, 3x, the whole thing is being raised to the 0 power. So it'll just be a 1. So like it says here in the rule, anything to the power of 0 is 1. It doesn't matter what it is. Anything to the power of 0. No matter how complicated, as long as the entire thing is being raised to the 0 power, you're going to get a 1. On the other hand, though, in part D, since there's no parentheses, only the x is being raised to the 0 power. Not the 3. The 3 is just kind of along for the ride. Raised to the 0 power. So you can kind of think, well, the 3 is just kind of sitting there waiting to see what happens to the x. X raised to the 0 power is 1, like we've seen. So it ends up being really 3 times 1, which is 3. So be careful. Parentheses really make a difference. Putting it around the 3x makes the whole answer 1. But no parentheses means only x is raised to the 0 power. That'll make x to the 0 power 1, but the 3 is still there being multiplied by the 1. Alright, that sounds good, I think. Hopefully it makes sense. We got another rule. I know this is a lot of rules to throw at you, but the more of these you practice, the better you'll get at them. It's hard to kind of keep track of them and which one's which. When do I subtract the powers? When do I add them? And here's another one. So what if you have one base with 2 exponents? So notice, just to be careful, notice the difference between this and the product rule. The very first rule we had in this section was the product rule. And it looked like a to the m times a to the n. But notice we're not starting with 2 separate a's, it's just one a. So you have one base with 2 exponents. Whereas the product rule, you have they're the same base, but you have 2 bases next to each other with 2 exponents. But ours is different. We only have one base with 2 exponents. So if you want to raise a power to a power, that's kind of what's happening here. You multiply the exponents, but don't change the base. So it's confusing because the product rule, you added the powers, remember? So if you have 2 different bases, 2 separate bases, I guess. They're the same base, but they're separate. A times A. That's when you add the powers, but when you only have one base, A, to a power, then you multiply the powers. So let's try that here. For the first example 4, part A, we have g to the 2nd power, and then that to the 9th power. You don't have to write the step out, but if you want to be careful, It's the first exponent multiplied by the second exponent. So g to the 2 times 9 would be 18. That would be your answer. And notice the difference, or I guess if you're wondering, well, when would I add those powers? You would add those powers if you had g to the second power times g to the 9th power. So notice there are two separate g's there. That's when you would add them. It would be g to the 2 plus 9 is 11. That's different. So remember, if you have two separate bases, like g times g, that's when you add the powers, but we were just given one base, g, and two exponents. So keep the difference in mind. It really means, yeah, it'll be different. You're not going to get the same answer. Notice one of them was an 18th power, one was an 11th power. So anyway, don't think of it as the same rule. It's a different rule. All right, so our answer there was g to the 18th. Now part B is a similar thing, but your base is a number. So it's 3 to some power. The power is whatever the first exponent 4 multiplied by the second exponent 15 is. See, 4 times 15 is 60, I believe. And that one for sure, don't worry about raising 3 to the 60th power. I think actually that exponent's so large, if you try to do that on your calculator, you get an error. So you couldn't even be able to handle all those digits, I don't think. All right, I mean, seems like there's a lot of rules here, but sorry, they'll be really helpful in the future. So okay, the next rule, the power rule. Let me just see the power rule. Huh, all right, sure. Maybe this is another power rule. I thought it had a different name. Oh, well. Another rule, okay. So it says, I guess it's like, we haven't seen this before. Notice you have parentheses around A, B. So you kind of have two different things multiplied together in parentheses, whatever A and B are, and you're trying to raise that to some power n. So I guess the idea is you are able to distribute the power n onto either of those. So if it's something times something inside parentheses, and that's the whole thing's being raised to the power, you can distribute that power onto either item. No problem. So let's see, let's try that on part A here. So notice inside the parentheses we have 4 times x, and the whole thing, 4x, is being raised to the third power. So I'm able to, if I want to, distribute the third power onto either of them, making it 4 to the third power times x to the third power. And you know, this might be one where 4 to the third power might not be a huge number. I might write that out. 4 times 4 times 4. Let's see, 4 times 4 is 16. Times that last 4 makes 64. Okay. And of course, x to the third, I can't do anything with that because I don't know what x is. That's kind of as far as I can go on that one. So sometimes it's kind of hard to tell. Do they want me to write that out or, you know, actually evaluate that 4 to the third power? I think if the exponent is somewhat small, like maybe 4 or smaller, 4, 3, 2, 1, then you can evaluate it. But like the last one we had, what was it, 3 to the 60th power? Yeah, that exponent is way too large. I don't think they'd want you to evaluate it. It's too big. Okay, let's try part B here. So it looks more complicated, but we still have two things being multiplied in the parentheses. It's -4 times t to the 9th. So I'm free to distribute the second power onto the first item, -4, and then onto the second item, t to the 9th. I think in this one, though, I might use parentheses around the -4 since it's negative. So be careful. I'm going to make sure, because it's not just 4 being raised to the second power, it's -4 being raised to the second power. And I might use it around t to the 9th as well, because I'm just kind of worried about how that t to the 9th power, and the square, or the second power I'm giving it, are going to interact. And let me simplify these guys. So since -4 is in parentheses, that means -4 squared, that's -4 times -4, which is positive 16. And if I didn't put parentheses there, I might have mistakenly thought the answer would be -16. So be careful. It's not a bad idea to use parentheses, especially since this part B here compared to part A is so much more complicated. And then as far as the t goes, this is a power to a power, which that means we're going to use that last exponent rule that we had. If you have a power to a power like that, there's only one base. You're going to multiply the powers. 9 times 2, so you'll get t to the 18th on that one. 16t to the 18th. Okay, looks good to me. Alright, last one in this, for this rule. This one looks really complicated. You have, in the one parentheses, a to the 5th times b. That's actually being raised to a power. So I'm probably going to be using this rule that we just learned to distribute that third power onto either of those. And then I'm multiplying that by more a's and more b's. Although these ones don't have an exponent here. There's no exponent to worry about. But I think eventually what I'm going to want to do is combine these a's and then combine these b's as well. But I'm not going to be able to do that because I think kind of the a's and the b's in the first parentheses are trapped because they're being raised to the third power. So I can't have any hopes of combining the a's in the first parentheses with the ones in the second parentheses until I know what to do with this third power here. So I think I'd have to distribute this third power onto either the a and the b, and then I'll think about later how those interact with the other a and b. So let's see. You don't have to write as many steps as I do, but I'm just going to be really careful. It was a to the fifth, that's being raised to the third power now, and I'm distributing that third power onto the b as well. And I think since the b didn't have anything interesting happening, there was no negative, it didn't have an exponent to begin with, I don't think I really need to put the b in parentheses. And then once I simplify what that is, I'm going to multiply that by the other parentheses, but I'm going to try to simplify the stuff on the left as much as I can first. I have a to the fifth, and that's to the third power. If you have one base raised to two exponents, you multiply them, 5 times 3. And then there's nothing really happening with the b to the third. And the guys in parentheses on the right side are just kind of waiting to see what happens with this a and the b on the left. So it'll be a to the 15th, because 5 times 3 is 15. So that stuff times a to the 7th, b to the 11th. Alright, and this actually looks like, I think it was part C from the very first example. We're going to kind of multiply. We wrote out a lot of steps before, but we saw that you can just multiply the a's together. And this one's different. You're not going to multiply their exponents because there's two separate bases. If you want to be careful, maybe I'll write it out. It's a to the 15th times a to the 7th, and then b to the 3rd times b to the 11th. That makes it more clear. I see that there are two separate a's there. So I know it's not going to be the same as, I guess, like this guy here. This was a to the 5th to the 3rd. There's only one base there, so you multiply the powers. But here I have two separate bases, a times a. So I'll be adding the powers, 15 plus 7. And then the same thing with the b's. There's two separate bases, so I'm going to be adding 3 plus 11. So it must be a to the 22nd power, b to the 14th power. Whew. That's probably as bad as these problems get. That's pretty complicated right there. Okay, I think that one sounds good. And we're almost done with this section. I know this is a lot of rules to take in. Sorry about that. But I promise they will be useful later and very important. So our very last rule here. It doesn't really have a name. It's kind of a tongue twister. Raising a quotient to a power. That's kind of a complicated name, right? So okay, you got a quotient to a power. So we haven't seen this before, although it does look like a lot like the last one. What was the last exponent rule we had? It said a times b in parentheses raised to the n power, and we said you can kind of distribute the n power onto both a to the n, b to the n. And you know what, actually, now that I see that, I wanted to mention something. Let's say you had a third example, like we had a part A, part C, part A, part B, part C. Let's say there was a part D where they said, what's, I don't know, x plus 3 to the 2nd power. Well, if I was looking at those previous examples we did, where are they here? So like, how about part A, we said, oh, it's 4x raised to the 3rd power. I'm going to distribute the 3rd power. If you try to distribute the 2nd power here onto the x and the 3, that will not work. No, this is not equal to x to the 2nd power plus 3 to the 2nd power. So be careful, you can't use this rule as a general rule. Notice that this rule up here, it only shows multiplication inside the parentheses. It's a times b to the n. If you have a plus or a minus, it will not work. So to keep that in mind, that's very important and something that students forget all the time, and they try to do that. As a matter of fact, when I teach calculus 2, the second calculus, students are trying to do that all the time. They forget always. So try not to be that guy or that girl. You cannot distribute an exponent across addition or subtraction. That's a no-no. But it's something that everybody wants to do. It seems like a good idea, but it's way more complicated than that. But we are, from the last problem, the last rule, we are able to distribute it across multiplication. If you're multiplying two things and the whole thing's being raised to a power, you can give either of those things its own exponent. And then we see in this next rule that we haven't quite talked too much about yet, if you have two things being divided in parentheses, a divided by b, and the whole thing's to the n power, then you can distribute the n power onto the numerator and denominator. So if you're multiplying or dividing and you're raising it to a power, you can distribute, but be careful, because if you're adding or subtracting inside the parentheses, you cannot distribute. We'll have to see what to do in future sections, not this section. Okay, so let's see if we can practice that. So we have in part A here a fraction y over 4, and it's all to the third. Since they're dividing, this is exactly what we see in the rule. You can distribute the third power onto the numerator, distribute the third power onto the denominator. And this might be one where the denominator, 4 to the third, that's kind of small enough that I think I can actually write that out. And I kind of memorized, I think we did 4 to the third power a little earlier. 4 to the third power, 4 times 4 times 4 is 64. I think that one's small enough that I'm okay I don't feel bad writing that out, or I don't think I'm doing too much work. Okay, that sounds good. Let's try the next one. I see that it's a fraction of 6 over z to the fourth. Well, since they're dividing, or since it's a fraction, I'm free to distribute the second power. It's going to be, 6 to the second power on top. On the bottom, though, I want to be careful. Z already had a power, the fourth power. Now it's being given another power, a square. So you might want to write that intermediate step of writing it out. And now I can tell that looks a lot like that power rule, because it's z, one base with two powers. You multiply the powers, 4 times 2. You can just write 8 if you want, but I always like to be really careful. 4 times 2 is 8, so the denominator will be z to the 8th. And the numerator, probably 6 to the second power, is small enough that I think I can write it out. 6 to the second power is 6 times 6, which is 36. Alright, so this rule is pretty good, not too crazy. Let's try this last one here. So I do see it's a fraction. It's 3s to the 7th, that's kind of a complicated numerator, over t to the 8th. That's kind of a complicated denominator. But the numerator is really complicated. But still, it's a fraction. So we can do like this rule tells us to do, distribute the power onto the numerator. But because the numerator is so complicated, I'm going to be careful and write it in parentheses. It's that whole thing to the fourth power. And then the denominator is kind of complicated as well. T to the 8th is also being given a fourth power. And now I look at the numerator and I say, oh, you know what? This is actually that first, kind of the power rule before this, where it was something times something inside parentheses being raised to the power. I can distribute the power onto either of them. Because here we have 3 times s. So I can distribute the fourth power onto the 3 and onto the s to the 7th. So this problem is complicated. We're actually using two exponent rules in one. We first used this kind of raising a quotient to a power rule, and the previous one we used the raising a product to a power rule. So let me distribute this fourth power. 3 gets the fourth power, but the s to the 7th also gets a fourth power. I'm going to be careful and write that out. So s to the 7th and then to the fourth power. The denominator I've kind of already figured out. This is t, that's one base with 2 exponents. I'm going to multiply the exponents, 8 times 4. Okay, so I think we're almost done. This one's kind of debatable. I think 3 to the fourth power is small enough that I can multiply that out. 3 times itself 4 times is 81. So I'm just going to write that guy as 81. That's fairly small. That's not a huge number. And then s to the... This is another example of it's one base, s, with 2 powers, 7 and 4. I'm going to multiply those powers. 7 times 4 is 28. And then in the denominator we have t to the power of 8 times 4 is 32. There it is. I don't think it gets much better than that. That's kind of as simple as it gets. Alright, I think that looks good. Now these last examples are just kind of a hodgepodge or kind of a random mix of all the rules together. So these are kind of the more interesting ones. You have to determine which exponent rules to use when. So might as well start with part A. Let's see, we have... Oh, this one's kind of misleading. Notice it's this big old fraction. It's 5a to the 7th. That all over 2b to the 6th c. So I'm like, oh, that looks really complicated. I don't want to do anything with this. But notice the whole thing, the entire fraction is being raised to the 0 power. So the whole answer is just 1. Isn't that crazy? So remember that exponent rule, it said anything to the 0 power is 1, no matter how complicated. 0 power is 1. Yeah, it doesn't matter how complicated it is, I guess, as long as it's really the entire thing being raised to the 0 power. But let's say if it was something more complicated like 5 and then everything else without the 5 was being raised to the 0 power. Okay, that would mean only the thing being raised to the 0 power is 1, but there's still that thing in the front. You know, so I guess if you're not careful, you might, I don't know, you might say, oh, it's 1 when it's not, but as long as the entire thing you're given is being raised to the 0 power, nothing left out, everything being raised to the 0 power, then the answer is going to be 1, no matter how complicated the thing being raised to the 0 power. So that's kind of nice. I think you're going to like that. A lot of problems look crazy, complicated, and scary, but they're not, so. Okay, how about the next one? Let's see this guy. You got -3 to the 1th, -3 to the 1 power, subtract -3 to the 0 power. I think I'm going to think this one, there's kind of a lot going on, so you might want to use PEMDAS, the order operations, you know? What's in parentheses, what's exponents, what's being multiplied or divided, what's being added or subtracted. Because there's kind of a lot going on here. There's subtraction, there's powers. Okay, so first thing, parentheses. Within the parentheses, there's not really anything I can do. Both parentheses just have a -3. Nothing to add or divide or anything like that. But the exponents, I should do that next. I'm going to try this one. -3 to the 1 power. Well, anything to the 1 power is itself, so that's just -3. There's not really a need to, a need to write it in parentheses. And then subtract. Okay, now I want to figure out this guy. -3 to the 0 power. Well, we said anything to the 0 power is 1. So he's a 1. And the negatives, these two negatives do not cancel because the second negative is part of what's being raised to the 0 power. So that second negative, together with the 3, disappears and becomes a 1. But the first negative was not being raised to the 0 power, so he does not disappear. It's only the negative that was being raised to the 0 power that disappears with the 3. And now it just comes down to, alright, I don't have any multiplying or dividing, but I do see subtracting, so I'll do that last. -3 minus 1 is -4. So that was kind of a surprising answer to this problem, huh? We have -3 to a couple powers, and somehow you get -4. But, hey, crazy things happen in math, you know? Alright, this last one is probably as complicated as they get, I think. Or actually, that part C from the previous one's pretty complicated. Oops. Pretty complicated, too. This guy, he was pretty bad. But this one's probably is... If you can handle this last one, then I think you're going to be fine for this section. Alright, because we're going to have to use quite a few exponent rules here. So I'm going to look at what we're given. We have this fraction to the 3rd power. So there's a lot going on, you know. There are numbers and variables and things multiplied, things divided. But overall, this is a fraction. That's kind of the main thing that's happening. So the first thing I'll do is I'll distribute this 3rd power onto the numerator and the denominator. The entire numerator, -4p to the 5th, gets its own 3rd power, and so does the denominator, 3m squared n to the 3rd. That gets its own 3rd power as well. And then from there I'll see what to do. Well, we've seen this, that was kind of the, what was it, a quotient to a power? I think they called that. That doesn't really have a nice name or ring to it. This one's more like, now you have a product to a power in the numerator and the denominator. So here it's two things being multiplied, 4 times p, that's being raised to a power. Down here you have 3 things being multiplied, 3 times m times n, that whole thing to the 3rd power. But the product to a power, that rule said you're able to distribute the 3rd power onto either of the things in the product. So the numerator will become the -4, the first guy will have his own 3rd power, and the p to the 5th has his own 3rd power. And then similarly with the denominator, you have 3 things being multiplied, all of them get a 3rd power. So the 3 gets its own 3rd power, the m squared gets its own 3rd power, and then the n to the 3rd gets its own 3rd power. I'm going to be careful here. M squared gets its own 3rd power, n to the 3rd gets its own 3rd power. And I think we're almost done, because I've kind of step by step taken that very outer exponent and brought it on to every item individually. And now it's just a matter of simplifying. So in the numerator here we have -4 to the 3rd power. If you want, you can kind of think off to the side. That's, since it's in parentheses, it's -4 multiplied by itself 3 times. Let me see, 2 of those, -4 times -4, that's positive 16. But then times that last -4 makes it -64. So that would be your kind of your constant in the numerator, -64. Oops. Alright, and then for the p portion, you multiply the powers. Because remember, if you have 1 base and 2 powers like we have, you multiply. 5 times 3 is 15. Okay, the numerator is as good as it's going to get. It's not going to get any better than that. The denominator now, you have 3 to the 3rd power. 3 times 3 times 3. Let's see, 3 times 3 is 9, times the last 3 is 27. So that denominator will be a 27. And then for m, it's m to the second power to the third power. Similarly to p, you're going to multiply the powers. 2 times 3 is 6. And then the last guy you got, okay, n to the third, you're going to again multiply those powers. 3 times 3 is 9. And there it is, and that's as good as it gets. I can't simplify that. I guess I would look at the 64 and the 27, say, oh, can that reduce 64 and 27? No, nothing divides into both of those, so you're doing good. It looks perfect. So I know that was kind of a lot to throw at you. That's a lot of rules, and I know people in real life, rules aren't that fun. A few rules are good, I guess, in society, but too many rules make things no fun anymore. Am I right? You ever played a really complicated board game? And it was fun until you read the rule book and it's so complicated, you said, never mind, I'm throwing this game away, it's too complicated. Kind of almost feels like that, but I promise these will be useful later and it'll help us feel more confident with polynomials, which is what we're trying to build up to. Okay, thanks for paying attention. I'll see you in the next section. Have a good day. Bye.